All right, section 2.2, we're going to take a look at describing sets in this section. And to start with, for our leading idea, set theory offers a foundational framework for organizing, classifying, and understanding relationships, skills vital in making sense of the world. Studying sets and their structure reminds us of the intentionality and order in God's creation. Integrating faith with mathematical thinking helps us view even abstract concepts as part of a larger design, inspiring thoughtful teaching and a deeper appreciation for the coherence and unity in both mathematics and creation. Let's pray. Dear Heavenly Father, I thank you for this opportunity. Thank you for allowing us to be here today. I pray that you would be in our classroom discussion, that as we're working together on new material and then also working on group work from the material we completed last time, that we would be able to pull together details and make more sense of what we're working with. We pray in Jesus' name. Amen. I'll do the role stuff later. Let's get started. All right, some vocabulary. First, if we're going to talk about something called sets, we better talk about what they are. So a set is simply a collection of objects. That's pretty vague, but that's what it is. And then the elements are those objects that it's a collection of. Okay. So this set could be a bunch of numbers. We're going to see some number sets. It can also be groups of people. Like we could talk about the set of people in this classroom. You guys would each be an element of that set. It can be something that is sort of, like the contacts in your phone, or, the songs that you have in your playlist. That can be a set. So anything where you're collecting a bunch of stuff is a set. And the items in that set are the elements. So there's two ways when we're talking about mathematical, like with numbers specifically, and also this first one works for the other items as well, that we can describe sets. The first one's called the listing method, and the second one is called the set builder notation method. So the first listing method is something like this. I'm going to give you an example. Both of these notations have curly braces. Okay, so you're going to start out with a curly brace. And we're going to do a few numbers. So I'm going to do 7, 8, 9. So the listing method would be actually listing them out. So I could do the listing method with you guys. I could just write each one of your names inside of the curly brace. That would be the listing method for this class. It's essentially my course roster, right? Without me on it. So listing method works as a general thing for all things. But imagine instead of this stopping right there at 9, it had said like this. Feel free to write it or not write that next to it. So it had sort of continued. Well, there's some limitations then with the listing method, because I can't list something that continues on to infinity, right? Like there's no way to actually list them all out, agreed? And let's say even it didn't go to infinity, it just went to say like 352. Well, I still don't want to list them out to 352. So like it's possible, but not practical, okay? So there is another method that kind of deals with that more effectively than this idea of the listing method. And this is set builder notation for this one that's listed here above. It's going to look like the same thing. And it looks like this. So you do a curly brace. I'm going to write out all the notation, then we'll talk about all the pieces, okay? So this is an X, a variable X is what we typically use. You could use a different letter if you don't like X. And you take and put a vertical bar, okay? Looks like a lowercase l, but taller or something like that, right? And then we have to describe two things about this set. The first thing we need to describe is what kind of numbers these are. So, and we can do this in either order. I can put that second if I want, it doesn't matter. It's just one of the two things. So the kind of numbers these are have a lot of descriptions. We could call these natural numbers. That's one way of describing them. We could call them whole numbers. That's one way of describing them. We could call them integers. That's one way of describing them. Any of those are correct interpretations of these particular numbers. Notice what it doesn't include. It doesn't include, like negatives. Negatives aren't in this list, right? But more pointedly, it doesn't include things that are between them. Like there's nothing listing between 7 and 8. So I don't have any of the fractions or decimals that are in between those, right? So I somehow have to convey that those are not allowed. And so there's two things I'm going to do. One I'm going to do is I'm going to say that the X values are greater than or equal to 7, right? Started at 7 and went its way up. Okay, values after 7. And the second one is that we're going to say that X, this symbol that's curled with an E right here, means is an element of. And I'm going to use natural numbers, but you could use a couple other things here as well. Instead of natural numbers, you could use a W, it's whole numbers. You could use a Z that's integers. And I don't think we've actually talked about those symbols yet. Is that true? Have we not? We have not yet. Okay. So these are symbols. These three especially are, well, two of the three here are very nice. Natural kind of makes sense that it would be letter N. W, whole, kind of makes sense as well. Z is integers. That's actually coming from the Latin, just so you know. So that's why we're not using the letter I, as they use Z for the Latin part of it. The one that's most natural to use here probably is the one that I wrote. X is an element of N, but any of the others will work. Okay, so we'll come back to some of that notation stuff in a little bit, okay? Actually, it's the next thing on my list. I apologize. How about right here? Symbols, used in set builder notation. All right, so the first one I'm going to use is I'm going to put this E with the line through it like that, or this C with the line through it like that. It's an E. This means is an element of. And what do you suppose it means if I draw a line through it? Yeah, it's not an element of, right? So for example, over here, the one that I just did, I could say that 8 is an element of the set. I'll just put it like this down here. It's the set moved down. 8's one of those things, right? But if I go down below and I would say, okay, but like 4, can't see that at all. I use black. 4 is not an element of these items, right? So this is how those would be used, those symbols. So that's the first one. The next one I'm going to talk about is the ones that are mentioning, that I mentioned after that, that are the letters. So N is the natural numbers. Natural numbers are also called counting numbers. So when you first start learning to count when you're little, what do you start with? Don't overthink this. It's not a trick question. 1, right? 1, 2, 3, right? You don't start with 0. I mean, 0 is a perfectly valid number, but we don't start with that when we're first learning to count. And we definitely don't go 1, 1.5, 2, 2.5. We don't do anything like that, right? So these are the natural numbers. They're the ones we first naturally start counting with. And I will write out some listing method kind of idea so we have a reminder of what those are. So these are the numbers 1, 2, 3, 4, and so on indefinitely. Whole numbers is next. Whole numbers are almost the same as counting numbers, or natural numbers. They just include 0. So whole numbers include 0, natural numbers don't. Okay, so far so good? All right, the third one I mentioned on the previous slide is integers. Okay, so integers are these positive numbers we had, but they also include the negatives that are sort of the reflection of those. So if we start out with a dot, dot, dot here, I'll do -3, -2, -1, 0, 1, 2, 3. It continues on in both directions, all the positives, all the negatives of the whole numbers. And it includes 0 too. It definitely still includes 0 because these are integers. There's 2 more we're going to look at. We're going to look at Q. Q is the rational numbers. And numbers, rational numbers, excuse me, are numbers that can be written as a fraction. So it includes the whole numbers, right? Let's say we had the whole number 3. How do I write it as a fraction? 3/1. I could do that, right? And it can be written as a fraction. It has to be a fraction of like whole values on top and bottom. For example, if you had, I'm going to give you one that's not rational, square root of 3. I can write square root of 3/1. That is a fraction, but it's not a fraction with the top and the bottom that are rational, like integer numbers, right? Square root of 3 is not an integer. It's not in this list, okay? And the reason that we use the Q is because Q stands for the word quotient. You've heard quotient before. What does quotient mean? Division. And that's what fractions are, is it's a division of numbers. So that's where the Q comes from when we use quotient, or use the Q for rational numbers. It's coming from quotient. And particularly the reason that we don't want to use R is because R has another name, or another value that it represents. R is the real numbers. So real numbers are all rational and irrational. Now, you'll notice I didn't actually put irrational up here. We're not going to discuss irrational in great depth or anything like that. There's actually not a symbol for it. That's the reason it's not on this page, is there's not a symbol for irrational. But irrational numbers are things that are like square root of 3, or pi, or maybe you've seen e before. They are numbers that do not terminate. It means they don't stop, and they also don't repeat. Right? Pi, right? We talked about pi recently, 3.141592, and it keeps going, and there's no discernible pattern that shows up. There's no repeating that shows up. It just continues to, feels like arbitrarily, right, extend with bunches of different numbers. That's going to be something that's irrational. All of our rational numbers have the ability to be written as a fraction. You can also think of it as a decimal or even a repeating decimal. Those are our rational numbers. Okay, so let's do an example. So our first example is that we're going to take a verbal description. It says write the set of natural numbers less than 5, and it asks us to do this in 2 different methods. The first one is the listing, or it's also called roster method. So the listing or the roster method is the one where we do both of them use curly braces, I should say that, right? But we just literally list them out. So what numbers are included in natural numbers less than 5? You can do them in order or not in order, it really doesn't matter, but what do I get? 1, 2, 3, and 4. Okay, so why do I not get 0? 0 is not natural. If it said whole numbers, I'd have got a 0, right? It's not a natural number. And why don't I get 5?
Because those are less than.
Yeah, it specifically said less than, right? Now if it said less than or equal to, then we would get 5. So pay attention to some of those nuances that we use. Set builder notation, we can do it for this. It feels a little bit funny. I'll just tell you that right now. It feels like overkill, and it is, okay? But it can still be done. So we do our X, we do our bar, okay? So those pieces will always be the same. This notation, that part of it means X such that, or it means like all values. That's what X means. It means all values such that, and then we're going to describe what kind of values it means. Now, I'm going to list them in reverse order for what I did last time, just so that you can see that that's okay as well in your notes. It describes these as all natural numbers. So we're going to say X is an element of the natural numbers. Okay, these are natural numbers only. And what else do we have for our description? Less than 5. So we would have to say that X is less than 5. Notice, I don't need to say that like it's between 0 and 5 or anything like that, because I already get the fact that it's bigger than 0 because it's natural numbers. Are you with me? Like that's not necessary. It's already confined to the positive parts of things and not including 0 because I said it was natural numbers. So this is overkill for this one, right? I mean, like it worked just fine to write 1, 2, 3, 4. But there are cases and there are problems where it's not overkill for. You can't even list them at all, okay? So we've got more than one notation. All right, equal sets. Equal sets are 2 sets that contain exactly the same elements. That seems like a very straightforward definition. But the reason that we have it is because we also have this one at the bottom that's called equivalent sets. And equivalent and equal sound an awful lot alike, and they don't mean the same thing, okay? So equal means we're talking about the same sets. For example, we'll do verbal description. If I were to talk to you about my children, right, my children, you guys have seen pictures before, and my husband were to come in here and he talked about his children, we would be talking about the same set of kids, right? I'm describing them as mine, he's describing them as his, but we're all still talking about the same 8 kids. Y'all with me? Those are equal sets. Now, they're also equivalent sets. Let me jump down to equivalent just for a moment, and then we'll come back up for a second. But equivalent doesn't mean that they have to be the same. It just means they have to be the same size. So if they're the same, right, my kids, his kids, they're still equivalent. but they're like more than that. They're actually the same. Now, if I talked about, let's see. If I talked about, I can't use my kids because I've got too many for this to work. Let me go to the one-to-one correspondence and I'll come up with something in the meantime. All right, one-to-one correspondence. One-to-one correspondence is a pairing of elements between two sets such that each element of one is paired up with exactly one element of the other. Now I've got my example. Told you I'd get there. Okay, so there's a one-to-one pairing. Okay, this is what happens and works really well when families get together with children. They want them to go play together, right? So if there's a one-to-one correspondence of children, everybody's got a buddy, we all play really nicely, and it doesn't work very well when there's an odd number of kids, correct? Yes, that's usually the way that goes. So when I was growing up, my mom had a really good friend. Her friend had 3 daughters, and they were very close in age to myself, my brother, and my sister, and then we had 3 of us. So there was a one-to-one correspondence. When we got together, everybody had a playmate. And for the most part, we got along pretty well because everybody had their own person that they hung out with. Not always even the same person necessarily, but we had our person that we got to hang out with because there was this one-to-one correspondence between the groups of people. Those 2 sets then would be considered equivalent sets because equivalent just means they have the same number. So my mom's kids and her friend Tina's kids, they were equivalent sets because they each had 3 kids. They had the same number. Okay, so equivalent means they're the same size, but equal means they're the same people or elements if we're talking about something that's not people. Do you understand the difference? Okay? They sound the same because in English, when we say equal and equivalent, we mean the same thing, right? So this is one of those nuanced kind of things that we have to be a little bit careful of in mathematics. All right. So we're going to take an example and look at how many one-to-one correspondences there are between 2 sets with 6 elements. So we're not doing my friends and my mom and my mom's friends groups of kids, right? That's 3 elements each. We're going to say there's 6 elements each, okay? And I'm gonna make up an example so you can see how this works, sort of a picture in your mind as we do it. Okay, so I want you to imagine that you're going somewhere and there's 6 women that go and there's 6 men. Okay, everybody got a picture in your mind? Maybe you're going to go out to dinner, maybe you're going to go to a dance, but somehow there needs to be a pairing of people showing up where there's 1 guy and 1 girl in a pairing. Got that? That's what's going on here. It's 6 guys, 6 girls. But we want to figure out how many different ways we could pair up the men and the women. Okay, still with me? Okay, so let's pretend we have gentleman number 1 who walks in the door. Okay, the ladies, you're all in here. Okay, so you're one of my 6 ladies. I know we got too many for 6, but just pretend there's only 6 of you in the room. There's 6 ladies in this room, okay? And one of the gentlemen walks in, and if it's arbitrary, like maybe he just doesn't know anybody in the room, whatever, and he's arbitrarily assigned or choosing someone that he's going to take out to dinner or dancing or whatever it is, right? How many choices does he have? 6. He has 6 choices. Now, that gentleman leaves, and he leaves with his date. They're out the door, okay? Gentleman number 2 comes in. How many choices does he have? 5. Why is it not 6? Because one of them already left on her date. Okay? So gentleman number 2 comes in. He has 5 choices. I'll tell you what to do with these numbers in a second. Gentleman number 3 comes in. How many choices does he have? 4. And how about the next guy? 3. Next one? 2. And our last gentleman? 1 or no choices, essentially. He's only got the 1 person to pick from, right? There's only 1 person left. Okay, so the way that we figure out our number of correspondences, and I'll draw a picture, and you'll see very quickly why I don't want to draw a picture of the whole thing, is that we actually multiply these values together. There's 6 ways the first person can do something, 5 ways the second, 4, 3, 2, and 1. So if you will multiply these out, 6 times 5 times 4 times 3 times 2 times 1. Grab a calculator if you need to. Probably you do. What are you going to get? That sounds too many. Try again. 720. Yeah, it should be 720. You might have gone 1 too big, Tessa. Yeah, there's 720. There are 720 different ways that those 6 people could be paired up and go out on a date. And is it any wonder that it's hard to figure all this dating stuff out? Like legit, right? Like that's crazy. That's 6 people. In our room right now, I didn't count, but if everybody's here, we've got 18. Or maybe it's 20. I can't remember the 2 classes. Like Like this is a weird thing, right? These numbers get really big very quickly. So here's the reason that this actually is difficult to draw, okay? So let's draw our six females, A, B, C, D, E, F, there's G, that's 6 of them. And then over here, we'll just keep going. We've got H, I, J, K, L, M, and N. Nope, I think I only needed an M. Yeah, that's enough. So there's 6 and 6. So what we would actually be doing if we were trying to sort of draw this out, and this is why I don't recommend necessarily doing this, is that we would actually have to draw between every single pair like this. Right? And then we go to the next one. And then we go to the next one, then we go to the next one, and it ends up being a very convoluted or crazy looking picture, right? Because there's 6 right here, and then once I'm done with those 6, I would do the 5, and then once I'm done with those 5, I'd do the 4, and it ends up being very messy. So this kind of a picture where we're multiplying them out with sort of these space holders tends to simplify the image pretty well. So we have 6 people for the first selection, if you will, 6 items for the second, 5 items for the second selection, and so forth all the way down, right? Now there's some examples in your group work and homework where it's going to give you some very detailed specific information. Like it's going to say something like this, that you're trying to pair up, I think it's letters and numbers or something like that, but it gives you something where it says, but A has to go with the number 5. Okay, so imagine, we'll back to our gentleman in the hallway, the 6 people walk in and one of them that walks in sees his wife in the room. He'd better take his wife out on that date, right? Bad idea to do anything different. There's not any choices, right? They're automatically paired up, and so they don't get included in these numbers, or you can say they're included as the number 1 because the choice has already been made. Yeah? So we just put a number 1 in that slot, and then we move on to the other people that have options still. That's how we deal with it if there's already a natural pairing that has to happen. Okay, cardinal number. Cardinal number is simply the number of elements in the set. And if our set is S, then the way that we write cardinal number is we write in, and then we put the S in parentheses. And sort of in our mind, we're naturally thinking this means number in S. It's the number of things in S. Okay, so my example a minute ago, if S was the group of ladies in the room, that would have been 6. There's the number of people in the room that was 6. Number of boys in the hallway was 6. Okay. A finite set is a set for which the cardinal number is a whole number. And an infinite set is a set for which the cardinal number is not a whole number. And by not a whole number, I don't mean like a fraction or a decimal, but it's too big to count, right? It's not actually possible to ascribe a number to it because it is infinite. And then the most interesting one on this page is the last one. It's the empty or the null set. So this is the set that contains no elements. You might think that doesn't sound very interesting. And it's written one of 2 ways. Therefore, since it has no elements, its cardinality is 0. It's written as a 0 with a line through it. So if your zeros already have lines through them, you need to stop doing that, please, because this is the notation for empty set. And if you write the notation that you're used to writing, maybe for a 0 with a line through it down, you've now written a notation that we're using for some other purpose. Okay, if that's you, be careful. This means empty set. There's another symbol. This symbol has another meaning in mathematics as well. Does anybody know what it is? It's an algebra meaning. Yeah, no, Lauren's right, it's no solution. So it can also mean no solution. But for the set theory, that part of math that we're talking about, it means empty set. Another option for how you can write these is curly braces with nothing inside. I think that one's actually very intuitive. It just looks like an empty set. It's a set that looks empty, right? It's great. Notice what I can't do. I can't take the 0 with a line through it and put it inside of the thing with curly braces, because then there's something inside there with the curly braces. It's the empty set. Okay? So don't merge the 2 notations together, one or the other. That's what we're looking for. So what we're doing next is we're actually going to be given some sets, and we're going to figure out their cardinality. So again, cardinality means how many items are in the set. Some of them are very straightforward. You could literally count them, or you can literally see them. Some of them require a little bit more work that feels like what we did in section 1.2, which was patterns, if you're remembering. That was patterns. So let's take a look at an example. Set A starts with 9, ends with 99, and it includes all the numbers in between, right? It says 9, 10, 11, ... So we continue in the same fashion, and we end at 99. This is small enough if you really wanted to count them, you could, right? Like I could go 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, and I could keep going all the way up to 99. I could do that. It'd be a bit annoying, I think. You'd run out of fingers and toes really quick, wouldn't you? You'd have to borrow your neighbor's friends and toes to count these things up. This wouldn't be very fun. There's got to be a better way to do this. Any idea how I could find, or what you think is, the number of items in this set, the cardinality? How would you suggest maybe finding them? Subtract? What do you want to subtract, Jordan?
99.
You are so close. 99 minus 9 is almost right. It's 8. It's 99 minus 8. And here's why. 9 is in the set. We don't want to subtract it out. So we subtract the value that came before it. Another way to sort of picture this is, let's say our number started at 1. We went from 1 to 99. How many numbers is that? Well, it's 99. And which ones are not included? Well, the numbers 1 through 8. That's why I'm subtracting them off. So this is 99 minus 8, which is 91. Fantastic. B. Tell me what you can see. What are these numbers?
Going up by 2.
They're going up by 2. We describe them in a certain way. Does anyone know what you describe these as? Evens. They're even numbers. They go by 2s. They're even numbers. And it doesn't look like they're skipping any, right? 2, 4, 6. They started at the beginning. They're ending at 2002, excuse me. How are we going to find the number of items in this one? Because I'm telling you, you might have wanted to count from 9 to 99, but you're not going to count from 2 to 2002. That's not happening. So how are we going to count these, or find this value without counting, I should say? Suggestions. What do you think? This is like what we did with Gauss, which was in section 1.1, actually, when we did that part.
Would you do 2002 divided by 2?
You would. So 2002, if it was just 2002, that would include the evens and the odds, right? But we're only supposed to be including the evens here. So we're dividing by 2 so that we only get the evens, because it's half of the numbers that we're getting included. What would we do if they were skipping by 5s? You divide by 5, right? However many they're skipping by is what we're dividing by here. So what is 2002 divided by 2? 1001. Okay, everybody good with that? Okay, C. C says it's a set of all x such that x is equal to 135 ... 99.
Why is that? What? Oh, wait, never mind. On ours it says x squared. Would that make a difference?
So that's a good question. There's a typo. I'll put my squared in there. Thank you. I'll fix it later. But to answer your question very specifically, no, it doesn't make a difference, actually. So it makes a difference in what the set is, but not how many items are in it. So let's make them match, and I'll show you why. So yours has an x squared. I think my paper does too, I'm sure, because I have the same paper y'all do. So this is actually describing the numbers that are 1 squared, 3 squared, 5 squared, all the way up to 99 squared. But notice that's the same number of items if they hadn't been squared, right? The squaring changes what the items are, but it doesn't change how many of them there are. Does that make sense for everybody? Okay, so I've got these numbers. They're all squared, but I go from 1 to 99. How many of them are there? Are there 99? You're skipping by 2s. And what did we say we have to do when we're skipping by 2s? Divide by 2. Now I want you to try that. What happens if you take 99 and divide by 2? What do you get? You don't get a whole number. What do you get? You get a decimal. Do you know what the number is? Does anybody know? 49.5. You get 49.5. Are there 49.5 numbers in this list? No, that doesn't make sense, right? There's a whole number of numbers. I can count them. So something is sort of off in what's happening here, correct? Okay, so let's actually go back up a step to the previous problem because there's something we didn't write down that's actually going on there. We started at the last problem with 2, which is the first even number, correct? On the previous problem, we didn't start at the first number, 1. We started at 9, yeah? So what did we subtract instead of having just 99 numbers in the first one on part A? We subtracted 8, right? Why did we subtract 8? Because it wasn't in my list of numbers, yeah? And that's why we chose it. That's why the 9 wasn't quite right. It sort of directed us to the right place, but it was still in the set. So we subtracted 8 because it was not in the list of numbers. Okay, everybody good so far? Okay, so what number within the pattern on B, let's go to B, within the pattern on B, what number is before the first number in our list?
0.
It's 0. So if I were to put minus 0 here, it is not going to change anything, right? I'm still going to get 1001. But what I'm doing is I'm taking off the first number, like before, I should say it that way, the number before our first number of my list. What kind of numbers is happening on part C?
A negative.
Before we get to that, what kind of numbers are these first?
Odd.
They're odd. They're odd numbers, right? So this is a list of odd numbers. So if I have to think about list of odd numbers, what number is before 1 in the list of odd numbers if I were to go sort of backwards? What'd you say?
-1.
It's -1. Everybody with me? So when I'm looking at the numbers that are going on top, what I really need is I really need the last number in my list, 99, and I need to subtract off the number that is before the first number in my list within my pattern. It can't be 0. 0 is not in that pattern. 0 is not odd. So I can't subtract off 0 there because 0 wouldn't be in the list anyway if the list continued in the other direction, but -1 would. So what happens when I do 99 minus -1? It adds it. And so what do I get? 100. And what's 100 divided by 2? 50. There are 50 items in this list. Okay, one more example and we'll pause and we'll do group work. D. Number of items in D. This says, this is the set of all x such that the values x solve this equation. X is equal to x plus 1. So what we're looking for is we're looking for any number that will solve this equation, a value for x. What x value will solve this equation? So somebody pick a random x value for me. Just a random value.
0.
0, thank you. What happens if I put 0 on the left and I put 0 on the right?
Doesn't work.
It doesn't work. Because what's happening on the right-hand side?
Always adding 1.
It's always 1 bigger than what I put in, right? So no matter what you pick on the left, the right-hand side's always going to be 1 bigger. What does that tell you? There is no solution to this equation. There is no number that makes it work. And because there's no number that makes it work, I heard somebody say, it's the empty set. This set has no solution, right? There is no value that makes this work. This is the empty set. So the number of items in set D, that is a D, it kind of looks like a 0. The number of items in set D is 0, right? Set D, if you will, is the empty set. But the number of items in it is 0, which is the definition of the empty set. And we can also look at it and say, there are 0 numbers that make this work. All right, so we will stop there for today.